Hi everyone and welcome to a new video about controller design. This is our example number 1 about the digital controller design. In this case we will discuss the P controller design. We will discuss the calculations for this specific example step by step and also verify these in Matlab simulations. So let's look at our example. We have the following system, which is our plant in the S domain, the Laplace domain, and we would like to have a digital controller in the digital domain which has a peak time in the feedback system of 2 seconds. So that must be after the unit step response. But before we move on, let's discuss what a digital or discrete time system is. So that is indeed also important before we move on in the actual problem. So if you have a system like this, which is a control of an antenna using in the analog domain using a potentiometer, which will then give a desired angle as the command, and the actual angle of the antenna is our output. And this is a simple expression of an analog control. But when you convert this exactly same problem to the digital domain, you need a command in between, which is a translation from the analog domain to digital and then the processing of that digital system, digital signals, and then process it back to the analog domain. For that we need an AD, which is analog to digital converter, and then also the digital to analog converter to get the real world. And this is the exact same procedure, but it is using different signals, and this is now the digital control. And for that we also give a command as an angle, but now we do it in the digital domain. So for the specific case, in a general way, we have a digital computer that is the controller itself, which is in cascade with the plant. And you see again the reference, the error, and also the output, which we here see as C. But you can make this more in detail by looking at the digital computer in great detail. You can see, okay, in the digital computer we also need to put in data, which must be a digital value. So we need to first convert our error signal from analog to digital domain. But in order to excite our plant, which is having some input, maybe a voltage, maybe a current, we also need to convert the signal or data from our computer, which is a digital signal, back to analog. So that is the two blocks we need in front and the back, as shown here in the block diagram, in order to have this digital controller complete. So the design step we will use for this example, for the digital controller design, are the following. First step is we will determine our design point from the specification in the S domain. And we did this also in the root locus design. So this is very similar. Then we will convert, since we want to go in the digital controller design, we will then convert our S domain representation of the design point in the Z domain representation. And that is the domain we will design our controller. Now from the controller parameters, we will set up the transfer function of the controller in the Z domain. So we need to determine also the controller parameters. Again, using the root locus method, using the loop transfer function. Now we will validate our controller if it is doing the job we want. Let's say the peak time in this case of 2 seconds, we are done. And we can then move on, and we will then check that, for example, using a simulation program like Matlab. And if required, we can still tune our controller to meet the required specifications by tuning maybe the gain of your controller or other parameter like the zero or the pole location. So this is the general outline I will use in this example, also in the next examples about the digital controller design for PI, PD, etc. So let's continue. Now we're specific part we want to have. So we would like to design a P controller for this plant in the digital domain, having a peak time of 2 seconds, and we will use a sampling period of 0.1 second. So the diagram is looking like this. So you see here the plant. Now we get actually more information. We have the plant here, and this is also the gain. We know this is familiar from our analog controller design. But now in order to have also the digital action, we need to sample this. So that sampling goes with a period of 0.1, or it is sampled with a frequency of 10 Hz, which is 1 over the sampling period. We also need to hold that value, and that holding operation is done here, and that is the transfer function in the S domain for that holding process. The holding can be done in many different ways. You can hold your sample here by having a horizontal line. You can also have it in a linear fashion. There are many different methods. I will use the zero order hold, which is this simple expression, and that will do the job for most cases. And if you want to have a very advanced part of it, you can move on and also do other parts of a holding. But this is good enough for this example. So we'd like to now know what this value of the amplifier gain K is. So we need to design this. So let's look at our solutions. First, as said, we look at the design point and we start with the S domain representation. Now we know the peak time must be 2 seconds. So the S domain representation for the design point is having a sigma d, which is our real value, and omega d, which is our imaginary value. Now the imaginary part, omega d, can be calculated now pretty easily and directly actually using this peak time specification, because the peak time is given by the omega d over pi. So we can rewrite this and get omega d, which is then pi over the peak time, which is pi over 2, also in radians per second. Now in order to get the real part, we need more information, but there is no information about, for example, settling time and other things. But when you plot the root locus of this plant in the S domain, having of course only the gain, we will see that the poles at 0 and -1 will come to each other and will leave each other at the average value of these two poles, which is the 0 and the -1. So the average value of the poles of the second order plant system is actually our design, the real value of our design point, which is 0 plus 1 over 2, which is the average, is a half. So this is what you need to use as the real value. So taken together, we have now our Sm, which is our design point in the S domain, which is minus a half plus j half pi over 2. So now, next step is the Z transformation. Now the exact transformation from the S plane to the Z plane is defined by this formula. So Z is equal to e to the power st, which this is then again the sampling period. But we have some issues here, and let me first discuss the planes first. So we have the S plane here. You can see the familiar S plane we have also discussed for the controller and also for stability analysis in the previous videos. You see three parts here, three regions. The A we know, which is the left half plane. The C is the right half plane, and we have also the B, which is on the vertical axis or the imaginary axis. In a similar form, we can transform these regions in the Z plane using the transformation by this formula. And then we have the A, which is here. It is inside the unit circle. This is a circle. And a B, which is here on the vertical axis, will come on that unit circle. So it is on that unit circle. And the C is outside that unit circle. So in summary, you have actually this table. And we know it is stable here, unstable there, and marginally stable when you're at the imaginary axis. And for this case, you have the similar conclusions. So the stable, imaginary stable, and unstable. And the table is summarizing this. So all poles are in the left full plane. Again, that means stable. And all poles in the Z domain in the unit circle means also stable. In this similar fashion, we can decide if it is also unstable or marginally stable. Getting back to this exact transformation, we cannot use this exact transformation directly in our analysis for two reasons. One, it is not a rational function, so it is not in fraction form like 1 over s or 1 over s plus 2, something like that. And it is also not compatible to be used in the transfer functions. So what we do? Now we can use an approximation. There are many approximations. One of the approximations I found it is convenient and easy to work with, and also in the math process, is the Tustin approximation or Tustin transformation. The Tustin transformation uses or approximates this relationship to a bilinear first order expression with a 1 pole and 1 0. So what does it mean? Now the Tustin transformation, the forward transformation, is given by this expression. So it's actually saying the following. If you want the S from the Z, which is then this value, so S is equal to 2 over your sampling time times this value here. So z minus 1 over z plus 1. But if you want to reverse that process, which is the inverse Tustin transformation, you can also get the z using your s. And this is what we will use. We will use the inverse Tustin transformation to get from the design point in the S domain, the design point in the Z domain. So that's our next step. So convert our design point in the S domain into the Z domain, and using the inverse Tustin transformation. So we then say Zm specifically is equal to 1 over the sampling period over 2 times the Sm over 1 minus the sampling period over 2 times the Sm. And Sm is shown here. So when you substitute that now in this expression, what do you get? Now you get here, of course, the 0.1 for our sampling period. The Sm is all shown here, so we have now substituted values. Now we need to simplify this because there are some fractions here. It is not really readable. So let's move on by multiplying the numerator and denominator by 20, because 0.1 over 2 is 1 over 20. So you can now get here 20 plus this, and then 20 minus this fraction, this part of the equation. Now you have this equation, which is more simple. And now you can also work out the parentheses by this minus sign. And this is the next step. And you can now again take the 20 and a minus half and 20 and a plus half. So you get now this expression. Still we can move on because there is a pi over 2 here, so also not convenient. So let's again multiply, and then this time using 2. So 2 times the numerator and 2 times the denominator. Then you get 39 plus j pi and 41 minus j pi. Now this is a very easy expression, but we need to have an expression which is in the form like this, not a fraction, so a real value and imaginary value. For that we can now use in this complex expression the complex conjugate method. So we can say let's now multiply the numerator and denominator by the complex conjugate of this one, which is the denominator 41 plus j pi, which is shown here. This is just a 1, of course. We don't change anything. We just add it here as a multiplication such that we can move on and have this form. So what you do is then you multiply out the parentheses here. So we get 1 by 1. The numerator is shown here. So it is 39 times 41, which is this one. And then 39 times the j pi is shown here. And then j pi times 41 is shown here. And then j pi times j pi. We'll get, of course, j times j is minus 1. So you get the pi squared only here. In a similar form for the denominator, 41 squared is 1681. But you get also 41 times the j pi, which is j41 pi. But you also have another one, which is a minus 1. And you also have the minus j pi times the plus j pi. And that will be then minus j times plus j is 1. And you get then only pi times pi, which is pi squared. Interesting thing here is also, that's the reason why we do this complex conjugate, is this is the 41 squared and this is the pi squared. So you actually get then 41 plus pi squared in the denominator when you do this action. So together you have this. So I combine now the values here. These are exactly j 80 pi, and you get 1599 minus pi squared. Now we can now get the real value here, approximate value here, and also the approximate value for the imaginary value here, and also this one. So that will be approximately this one. And now we can split these in the real and imaginary value as shown here. So using the rules for the fractions. Now taking this real, this imaginary here, and you have now our design point in the Z domain. So we have now transformed the design point in the S domain to the Z domain. That's shown here. Okay, moving on. Collect now the design points in the S and the Z domain here, and then when we move on, we now start by combining the sample, hold, and the plan transfer functions together. So the plan transfer function, hold, and the sampling. These are together, and that is given by the hold function first. This is the hold, which is gh here, and that transfer function will be now multiplied by the plan transfer function gp. That's shown here. The product here is just called g. And that is shown here, so it is 1 minus the e to the power minus st over s times the planned transfer function. And that can be done also or written in this form, so you will actually take out this numerator here and then have 1 over s squared times s plus 1, so because this s goes to the denominator here. We need to have the z transformation of this in the next steps. So the z transform of the sample hold and the planned transfer function will be then the g of z. So that's the z transform of g of s. So that means we need to take the z transformation as we did for the Laplace transformation like that. We need to have the z transformation. For that we need to look at the table. But before we move on, we can also split the problem or make the problem a bit easier by saying with this part here can be also taken out. And the reason why I take this out is because z is equal to e to the power st. And this is actually e to the power or z to the power minus 1. So that means this is just 1 minus z to the power minus 1. That's easy, so we have actually a part of the problem already fixed by this transformation. Only thing we need to do is the z transformation of this 1 over s squared times s plus 1, which is also shown here now. For that, you can use the partial fraction expansion, and you get now 3 fractions, and then look at the table of the z transformation going from the Laplace domain to the z domain. Now that part is quite lengthy and tedious. In this video I will just skip that. You can also check that really with Matlab and also do that for yourselves. Not really that difficult, but it is just lengthy, so I just skip that and give you directly the result for this transformation, including that 1 minus z to the power minus 1. This is now the z transform for our sample hold and planned transfer function together. Next step is using the root locus equation. As said, we use the root locus method. For that we use a design point. And root locus equation is the 1 plus the loop gain is equal to 0, in this case in the z domain. Now we have only the gain, k, the planned, and the planned of course in the z domains, and the controller is in this case just a simple amplifier. So we have this. Now we can now say gz is known, this is this, so we can put it here, and now we can express the k in terms of the other parameters in terms of z. Now we need to evaluate this z in the design point in the z domain, which is zm. So we need to substitute where we see a z, zm. I already designated that here, and now I will substitute that those expression here for the design point. Now we can simplify that because you see here 0.9398 and also minus 1, so we can take that together, and also other parts have the similar things. Let's do that, and you get now the final form of the expression for the k, which is our controller. Now we need to take that, the magnitude of this expression. So for that we need to make this minus a plus, so it is absolute value, and then use the value for the formula for taking the magnitude of this complex expressions. That's shown here. So we get the square root of the real plus the imaginary value, etc. Same thing for the denominator. This part is just what it is. It doesn't you don't have to do the square root problem operation there. Now, when you calculate that, you get now 2.65 for this gain. So using this gain amplifier of 2.65, we'll get our peak time of 2 seconds. That is our design. So our controller, proportional controller or P controller, transfer function is given by k is 2.65. Now let's check that. Let's go to the simulation. Before I move on, I will also discuss the Matlab script I have used for this example. I first define a Laplace parameter, which is then using this function tf. I also do that for the z, so the discrete time transfer function, which is then this. I then define my planned, which is then shown here, which is 1 over and then parentheses s times s plus 1. I have also the sampling time, which is t, 0.1, define just a parameter t. And then this is then the gz in the z domain, which is then given here. That means continuous to discrete time transformation. Now the first entry is our planned, which you want to transform in the z domain, so from the s. The second entry is our sampling period, which is now 0.1. And this here in the command like this is ZOH is the way you want to convert that, in this case zero order hold. And that is the command you also need to put here. You have also first order hold or other things, so you can also do that. You get also a different transfer function, and this is what I have used also in our example, so this is also what you need to do. And the k is then 2.65 because that was designed, and this is then the closed loop transfer function using this feedback command. Feedback command means the first entry is the entry here in the forward path, 1 is what you have in the feedback path, which is 1, and the -1 is here in order to get the negative feedback. If you forgot this, the MATLAB assumes that it is already by default negative feedback. Okay, this is the script. Now looking at the simulation results, first the root locus plot. You see here the poles, the original actual poles for this specific gain of 2.65. This is our design point. You see a 0.94 approximately and 0.15 as the imaginary value. If I look down here, the current location here for this pole, if I make now this, highlight this here, it is 0.946, which is close to that. And it is here 0.151 I, which is then our J, of course, in our calculation, and it is also very close to that one. So you can see it is really close and it's confirming our design point. Now when I look at now the simulation results for the transient response, which is the unit step response, you see this is really a discrete time system. See, it is sampling, it's not a continuous sampled continuous system response. You see here the value of the peak time, which is 2 seconds. There are also other information here, but it is 2 seconds, and that's actually what we wanted, so this is indeed correct. Other specifications, the performance of this is that the rise time is given here, the peak time is 2 seconds as required, also said before, so we have also the peak value. We see that the overshoot is quite high, 42%, so very large, but that is of course not a problem. We don't have any specification on the overshoot. Setting time is approximately 8.5 seconds, and also the final value is 1. That means there is no steady-state error in this problem. That is also not really a surprise because we have an integrator here and that is a pole at the origin, so that means we will have a 0 steady-state error. So the output will follow the input. So that means our design is complete. So we have achieved our goal for this specific problem. All right, this is our first example about the controller design using the digital controller. In this case, we just did the P controller using one specifications, the peak time, and we worked out the analysis for our design point and then move on to the Z domain and then find out our required gain. If you have any questions, comments about this example, please let me know. I will try to answer them as soon as possible. Don't forget to like and share these videos so that we can reach more people for these interesting topics. Thanks for your cooperation and see you next time in another video. Take care.